My series on mathematics specialist for the West Australian curriculum. Today we're going to be going over integration of trigonometric functions, looking at some different situations and the techniques that we can use to solve these problems. So first we're going to go over even powers of functions, specifically trigonometric functions of the form sine of ax plus b or cosine of ax plus b. And a and b are of course just constants. So for even powers, what I mean by that is just we'll have sine to the power of n of ax plus b, or cosine to the n of ax plus b, where n is just equal to 2k, and then k is a natural number. So if we have k equals 1, we'll have n equals 2, which is even. If k equals 2, then we'll have 2 times 2, which is 4, n is even. So that's what we mean by even powers of the sine and the cosine. So the two most important formulae that you must remember, these come up all the time in math specialist WACE exams, are the cosine double angle formulae. So I'll just write that down. So what these are, we have that cosine squared of x is equal to 1/2 times 1 plus the cosine of 2x. And then similarly for sine squared x, it is almost the exact same thing with the half and the 1 here. There will be a cosine 2x, but there is a minus here instead of a plus. So just get familiar with these and make sure that these two formulae are really implanted in your brain, because they will 100% come up all the time in your WACE exams. So we'll start off with a pretty simple example. What we want to integrate here, I'll just go example. We want to integrate sine squared of 2x and dx, of course. So using this up here, we know that sine squared of x is equal to 1/2 times 1 minus cosine of 2x. So what we need to do with this 2x is, this is essentially what this x is here, of course, so that will need to become the cosine of 4x, since this 2x needs to be multiplied by 2, like we have here. So by that will become the integral of 1/2 times 1 minus the cosine of 4x dx. That half can come out the front of the integral, which just makes things easier on the inside. So 1 minus the cosine of 4x dx. And then we integrate that. The integral of 1 with respect to x is of course just x. And then with this cosine, this will anti-differentiate to the same sign, so it's going to be x minus sine of 4x, but we need to remember the formula that we need to divide by the derivative of what is on the inside. So this is just going to come out to x 1/2 times x minus 1/4 times the sine of 4x. And don't forget the plus c, because this is an indefinite integral. So that's a pretty simple one. That's just going pretty much straight from the formula that we have up here, and a nice easy integral. Nothing too complicated here. But if we want to do something a little bit more complicated, so if we want to integrate the function cosine to the 4 of x dx, and so what we want to do here is we're going to want to use this double angle identity twice. So of course what we can do is we can just write this as cosine squared x and then all squared again. So that'll of course just, those powers will multiply and then it'll become cosine to the 4 of x. And then from before we have, so the inside of this integral is just going to be the same thing, so it's going to be 1/2 times 1 minus the cosine of 2x. Oh, brackets, there's a lot of brackets here, and then dx. Now this is just going to be a exercise in binomial expansion. So what I'll do here is take this integral again, and I might actually just expand this out so we don't have to deal with that a half in the front. Sorry, that needs to be bracketed since we're going to be squaring the whole thing. So that's just going to be a half minus a half times the cosine of 2x dx, and then this will be all squared. And then this is just a binomial expansion. So this is going to come out to the integral of 1 over 4. So we're going to square this. Well, we've already taken that quarter out, so that's just going to be 1. Then we'll get 2 times this, so that's just going to be a half. So that's, again, that'll just become a 2 because we've taken that quarter out. So 2 times the cosine of 2x, and then with this 2x here, we're just going to have a quarter cosine squared x, but we've taken that quarter out, so that'll just become cosine squared of 2x dx. And now we have to use this again, the double angle formula, because we have a cosine squared. So again, this is just going to be exactly the same thing. We're going to write this as a quarter times 1 plus 2 times the cosine of 2x. Using the double angle identity again, this is going to become a half times the cosine of 4x plus a half. That's basically just expanding. If you expand this formula out, it's going to be a half plus a half cosine 2x. So that I'm just going straight from there to there, and you'll see why in a second. I'm not actually going to use that big bracket. There's no need to. So this is just going to become a half times the cosine of 4x. Careful there, because we have the 2x in there. We need to multiply that by 2. And then we're just going to add a half. And then, of course, dx. Now, this 1 plus a half is just going to go to 3 over 2. We're just adding them. So we're going to go 3 over 2 plus 2 cosine of 2x. And then we're just going to go to the same thing, a half times the cosine of 4x. And then dx. And now we can just integrate. We can, we could take this 1/4 out if we wanted to, but we'll just leave it at the front since we know what we're doing by this stage, I hope. So this 3 over 2, that's just going to integrate to 3x on 2. So we're integrating cosine, the sign is going to change. So we're taking this, it's going to become cosine of 2 cosine 2x over 2. That 2 will just divide into 1. So we're going to be left with minus, I apologize, that is incorrect. The cosine will have the same sign when we are anti-differentiating. So this is just going to be plus sine of 2x, and then we're going to have a half divided by a quarter, which is going to be an eighth. So 1 over 8 times the sine of 4x. And then we are done with this integral. So that's usually the general way that we're going to do these. So if we have a 4 or a 6, you'll most likely only see a sixth power, nothing higher than that, because otherwise it just gets way too long to viably do. We'll get it into the form where we can use the double angle formula, expand, use it again, and then just integrate it normally. So I'm just going to get rid of everything on the page, and then now we're going to have a look at if we're using odd powers. So I'll just write at the top that we're doing odd powers. So this is where if we have sine cubed, cosine to the 5th, cosine cubed, anything like that. So the way we're going to do this here is if we were given the function that we wanted to integrate, if we had cosine to the 5th of 3x dx, what we want to use is break it up into a single cosine term, and then in this case we'll have cosine to the 4, because cosine of 3x times cosine to the 4 of 3x is just going to be this thing here. And then we're going to manipulate the Pythagorean identity, and we'll use some reverse chain rule to anti-differentiate. So this is just going to be equal to cosine of 3x times the cosine to the 4 of 3x dx. And then we know that this is just going to be, of course, equal to cosine of 3x. And in the same way as we did before, we're just going to call this cosine squared. We're not going to call it, it is cosine squared, and then all squared again. And then we know that the Pythagorean identity, cosine squared x plus sine squared is equal to 1. And then we're going to use that here. So if we move the sine squared x to the other side, that means that cosine squared x is equal to 1 minus sine squared x. So we'll write that down, and then we'll do a pretty simple binomial expansion. So this is then going to become cosine of 3x times 1 minus sine squared x, sine squared of 3x all squared dx. And then again, binomial expansion. This cosine of 3x is just going to stay. 1 squared is, of course, just 1. This will become plus 2ab. So that's going to be 2 times 1 times sine squared. So that's just going to be minus 2 sine squared of 3x. And then this minus sine squared of 3x is going to be squared. So that'll just become sine to the 4. Now, it might not look like we've made this much simpler, but once we expand this out, it will actually become considerably easier. So now we're literally just going to do a FOIL, as it's called. So we're going to do cosine of 3x times 1, which is, of course, simply cosine of 3x. And then cosine 3x times negative 2 sine squared 3x is negative 2 cosine 3x sine squared of 3x. And then once again, cosine of 3x times that sine to the 4 is just going to become cosine 3x times sine to the 4 of 3x. Now, what we need to remember here is that if we have an integral that is of the form f dash of x to the n. So if we have a function raised to a power and the derivative is outside of the function, we can use the reverse chain rule to get this result. So this is, again, just the power rule over n plus 1. So if we can manipulate these into that form, or if they already are, we can just simply use this identity here. So what I'm going to do is I'm going to split this integral up into its, just by linearity, minus the integral of cosine 3x. Sorry, that's going to be a 2 there. Minus 2 cosine 3x sine to the, or just sine squared. And then we're just going to have this integral, which is this bit cosine 3x sine to the 4. All right. So this is good. This is what we want. So now what we're going to do is just a little bit of algebraic manipulation. So what we also need to remember here is that if we have the integral of a times f of x dx, where a is just a constant, that implies, and well, is an equivalence relation with a times the integral of the function. So essentially what we can do is we can multiply the inside, if we wanted to here, we could multiply the inside by 3, and then we could take out a third, because when we multiply them, they're just going to cancel out and it's going to be the same thing. So with that, we need to cast them on back to this form and manipulate each of these integrals so that they are of this form. We can use this formula here. So we're going to keep this integral the same because we have a formula on our formula sheet for that. But what we're going to do here is I'm going to take this minus 2 out. And what I'm going to do is I'm going to write 3 times a third of cosine 3x sine squared of 3x dx. Now the reason I've done that is because if we differentiate sine of 3x, we are going to get 3 times the cosine of 3x. And if we take this third out, we're just going to be left with the derivative of sine of 3x. And it's not the derivative of sine squared of 3x, it's just the function that's being raised to that power itself. So we'll get to that on the next line of working, but we're going to do the same thing here. I'm going to write this so we have, I apologize, that is a mistake up there. That needs to be the sine of 3x dx. I'm going to do the same thing here. So that's going to be plus the integral of 3 times a third of what's left. So it's going to be cosine 3x sine to the 4 of 3x dx. So now we're just going to manipulate these using this property up here, but we're going to choose what we actually take out of the integral. So the first integral stays the same, but because we want this 3 to stay here, because that's the derivative of sine of 3x, 3 cosine 3x, we're going to take this third out here and multiply it by this 2. So that's going to give us minus 2 over 3 times the integral of 3 cosine 3x sine squared of 3x dx. And then we're going to do the same thing here. We're going to choose which constant we want to take out. And here, it's going to be this third, because again, derivative of sine 3x is 3 cosine 3x, which we can get if we take this third out of the integral by the linearity of the integral, as I showed up there. So that's going to become a third times the integral of 3 cosine 3x sine to the 4 of 3x dx. And now we've got it into a form that is really, really easy to use. So when we anti-differentiate cosine, the positive or negative, it stays the same. Because if we differentiate the integral of cosine of 3x, we just get cosine of 3x itself. So that's going to become, and look on your formula sheet, don't bother remembering this, it's going to be a third sine of 3x. Now, we've got it in this form. 3 times the cosine of 3x times sine squared of 3x. So when we anti-differentiate this, the derivative kind of disappears. And that's by the chain rule. It will kind of cancel each other out per se, not literally, but it's a good way to remember it. So that 3 cosine 3x is not actually going to be anywhere in the integral. So we need to, by the power rule, and as that rule states up there, we need to increase this power of sine and divide it by the new power. And not forgetting that we've got this 2/3 at the front. So this is going to become, I'm not going to use a big square bracket, I'm just going to use a bracket like this. So that's going to be sine cubed of 3x over 3. So that's that integral done, and then we have the same thing here. We've got this third out here. The derivative isn't going to be in the anti-differentiated function, but we're still going to have that. We're still going to have that 1/3 at the front. So again, we're going to raise the power of sine by 1 and divide it by the new power. So we'll have sine to the 5th of 3x over 5, and then we're going to put the plus c at the end here. So noticing that we have a factor of 3 at the front, we're going to take that out just to simplify it a little bit. So that's just going to become the sine of 3x. This is just going to become minus 2 but this is going to be over 3, so that's actually still going to be minus 2 over 3. Because if we multiply those, we would get 2 sine cubed 3x over 9, which is equal to 2 over 3 times 1 over 3. So that's why this is going to stay here. And this is just going to stay as sine, gosh, I can't write at the moment, sine cubed of 3x. And then because we have this third here that we factored out, this is just going to stay the same, plus a fifth times the sine to the 5th power of 3x, and then plus c. So that's that integral done. A fair bit of computation, but it's not too bad once you practice it and you know what you're looking for. Yeah, so that's the odd powers of cosine and sine integrals. It's going to be the same thing for a sine integral. It's really just an algorithm. You break it up so that you have 1 power of the trig function raised to the 1, so just by itself, and then an even power. That'll just become cosine squared squared. Use the Pythagorean identity, expand, and then you'll be able to use the reverse chain rule to integrate quite easily. So that's that done. And what we're going to look at now is integrals that are of the form of both. Now, the great thing about this is that we can actually use some lovely substitutions. So I'll get rid of all of this and we'll look at our next little bit. So right now I'm going to look at the integral of sine cubed of 2x, cosine squared of 2x. And this looks daunting, I know, but using a few little tricks that we have up our sleeve from previous chapters, this actually isn't too bad. So to make things easier, what I'm going to do is I don't want to work with this 2x, it's going to be annoying. So I'm just going to let u equal 2x, du is equal to 2dx, and then we need to get dx by itself, so dx is just a half du. And immediately what we can do, these 2x's, they're all just going to become u, and this a half, I'm just going to take out the front of the integral because I don't want to work with it inside the integral. So with this, we're going to have a half times the integral of sine cubed u times the cosine squared of u du. Now, how we're going to do this is pretty similar to the last integral to try and get it into a form where we can use the reverse chain rule. So what we're going to do here is we're going to use the Pythagorean identity again, but for that we first need sine squared and cosine squared. So with this sine cubed, of course, that's just going to be equal to sine squared of u times the sine of u times cosine squared of u. And using the Pythagorean identity for both the just for the sine squared, so that we can use it for the reverse chain rule, we're going to write that sine squared u as 1 minus cosine squared u times sine u, and then times cosine squared u with respect to u. And now we just expand. So this is going to become we won't expand it with this sine u at the moment. We're just going to expand it with the cosines. So this is going to be a half times the integral of 1 times cosine squared, which is just, of course, cosine squared. Then minus cosine squared u times cosine squared u is cosine to the 4 of u. And we still have that sine u there, of course. And this is where we're going to be using the reverse chain rule. So after we've done that, we've got powers of cosine. We're going to expand it with this sine u as well. So a half times the integral of sine u cosine squared u. And then minus sine u times cosine to the 4. And I'm actually just going to write this as two separate integrals. So this is going to be minus, and not forgetting the half, because this is applied to the whole integral, it's going to be sine u cosine to the 4 of u du. Now, what we need to remember here is the signs, not the actual signs as in the plus or minus outside of the derivatives. So if we want to differentiate, and here it's going to be with respect to u because this is our variable. If we differentiate this, we need to remember that this is going to become negative sine u. So what we need with these signs, as in the sine of u, is we need a negative at the front here so that we can use the reverse chain rule, so it's in the form where the function that's raised to a power has the derivative of the function in the integral as well. So again, we're just going to use the linearity of the integral. We can just take this, we can make this a negative here, but we also need to make it a negative here as well. And if we take this negative here and we'll put a negative here, this is just going to become plus. So I'll write that again. So that's going to be negative a half times the integral of negative sine u cosine squared u du. And then because we're going to have a double negative here, I've put that negative in. This is going to become plus a half times the integral of negative sine u cosine to the 4 of u. And now again, this is really nice and easy to anti-differentiate because we have exactly the form that we need. So for this first integral, we're going to leave this half at the front. This is just going to come cosine cubed u over 3. So I'm going to write a third cosine cubed u. And then this is going to be the almost the same thing here. So that's going to become cosine to the 5th over 5. So then we're going to get, need to close that as well. So that's going to be a half 1 over 5 cosine to the 5 of u. And then this is going to be a plus c. So now, we can just expand this out if we want to. You could probably leave it like this, but it's probably nicer to leave it in, without all these yucky brackets. And so we'll write the positive first because, it'll look nicer. So this is just going to be cosine to the 5th of u on 10, a half times a 5th, and then it's going to be minus cosine cubed u over 6 plus c. But this integral is in u, and we need to now bring it back into in terms of x. So we can just directly go back here. We know that u is equal to 2x. So any of the u's that we see down here, we can just write as 2x, which is, of course, just going to be equal to cosine to the 5th of 2x all over 10 minus cosine cubed of 2x over 10 plus c. So these integrals, especially the trig integrals, they're really about just noticing patterns and noticing where you can manipulate the function in a way that'll make it easier to work with. Because definitely a lot of the time you can look at these and think, I don't even know where to start. So with these, it's really just practice, making sure that you've got a toolkit of techniques that you can use, because a lot of the time, with this one, we've got kind of like intellectual manipulation of it, we've got use substitution, we've got reverse chain rule. So, these integrals there's a lot to them, but they become more of a algorithmic process as you practice them more and more. So that's going to be the end of this video. If you found this helpful, I'm glad. And I will be continuing this series pretty soon. So stay tuned for that one, and thank you very much for watching.